Okay, so I want to take a few minutes now to tie back the strategic formation to some of the random network models we've looked at before, and in particular show how we can build an exponential random graph model that is based on strategic network formation. Okay, so we'll talk about fitting a statistical exponential random graph model. And the idea here is what we're going to need to do is add some noise to the strategic formation so that we end up with links that look somewhat random. But we want to allow the link and subgraph formation to depend on node characteristics, right? And let's show that if we build one based on utilities, that we can still fit that into the exponential random graph model. And so this gives us a way of then tying these two sets of modeling techniques together, and in particular, that'll allow us to do things like estimate welfare implications of certain networks, something that was missing from the random network model before and comes out of the strategic formation. And it also allows us to adapt some of the more rigid strategic formation models to allow them to be more flexible, have some noise in them, and actually match data. So it'll be a nice marriage between these two different modeling techniques. Okay, so how are we going to do this? We'll do it as follows. So let's let what we'll do is allow a given node to be faced with forming different potential structures. Okay, so for instance, it meets another node and it decides whether it wants to form a link, or it meets a group of 3 and decides whether it wants to form a triangle, or it meets in a group of 4 and decides whether it wants to form a clique of size 4, etc. Okay, so what it'll be faced with is a whole series of different subgraph opportunities, and we'll look at the utility of forming a given link ij as depending on some link parameter. So there's some value of links in general, but then it's going to be a function of the characteristics of I and the characteristics of j. So it could be that the given individuals care about their relative ages, or their education levels, or their match in terms of distance, something. So they've got a whole series of characteristics. Those characteristics enter into what the utility from forming that link is. And then there's some error, which could represent compatibility, or other kinds of characteristics that we're not observing. There's some independent error, which is going to hit just that particular link and say whether the utility ends up being higher or lower than what it would be just based on the observable characteristics. Okay, so we've got a random utility now. We just stick in the noise here, and that'll noise things up so we can fit it into a nice statistical model. But there'll be some basis of the value to that link based on the characteristics of the nodes. Then we do the same thing for a triangle. So what does I get out of being in a triangle with I, j, and k? It gets some value based on a triangle times a parameter on triangles, which scales up what the values are. And then also an error term for these I, j, k's. So now there'll be an error for each possible triple, saying whether this triple looks more or less attractive than a typical triple with the same characteristics to a given individual. Okay, and then we can build up whatever different subgraphs you might think of considering, cliques of size 4, or some kind of other network structure that might be important, or we could look at things that look like almost cliques of size 4, and so forth. So you could put in those and allow people to get value from those. It could be that people also get value from indirect connections, so they can think of how many of these situations where I'm I, that I'm connected to some j, and j has 4 friends. What's my value from that kind of configuration? And so you can stick in a whole series of different possible subgraph configurations, give them values and so forth, and that's going to be the basis for the model. Okay, so that's the structure. Then when we look at the noise, what we'll do is we'll have some distribution function, which on links, for instance, which gives us a distribution over the noise. And based on that, we can say, okay, I is going to prefer to form this link ij when the noise, the epsilon that it gets, is less than the value that it gets here. So if this is the value, we're subtracting off some error term. As long as epsilon ij is less than this, then the value of this is going to be greater than 0. Okay, so that's going to be the situation where I wants to form that link. So this is going to happen with a given probability. What's the probability? The probability is just the probability that this epsilon ij is less than this value, which is just the distribution function evaluated at the base value of the link to I. Okay? So now what we have is we have a probability that I is going to like the link ij when the characteristics of I are xi and j's characteristics are xj. And then we can do the same thing for what's the probability that I would like a triangle of a given set of characteristics, and whatever shape you've got, we've got a probability that I is going to want that. Okay. Now, if we think of forming what's the probability that then a given link forms, well, it's the probability that I likes the link, the probability that j likes the link, and some probability function which is going to describe what's the relative likelihood that this link is identified. So that gives us a base probability on links. Similarly, we can have a base probability on triangles, which is going to be the probability that all 3 individuals involved like the triangle times some probability that this triangle gets recognized or that these 3 people have an opportunity to meet. We could ultimately allow these things to depend on characteristics as well, right? So this could depend on xi and xj. This could depend on xi, xj, xk. So this whole thing is some function of xi, j, and k, and these probabilities could depend on those as well. Okay? So based on that, we have base probabilities of different graphs being subgraphs having opportunities to form and then people wanting to form them. So that gives us some basis for the probabilities. Okay, and then what we can say is the probability that, so now let's put it into a logistic form, so we'll be able to move this into an exponential form that fits to the exponential random graph models. Let's say that the probability that the link with characteristics xi and xj that this particular link would form is going to be proportional to the exponent of this base probability compared to the exponent of the space probability plus 1. Okay? So what this does is just put this in an exponential form so that things will nicely aggregate and we'll end up with a form which is represented as an exponential random graph model. But this is sort of adding an extra layer of noise on top of these base probabilities, shaking those up and putting it into an exponential form. So the higher this probability, the higher the probability that this actually forms, and the lower the value here, the lower the probability that this actually forms. Okay, and then we've got probabilities on the triples and so forth as well. And so the larger these values, we end up with high probabilities of it forming and lower values, low probabilities of it forming. So we take all these, and now if these were the probabilities of each link forming, each triangle and so forth, now we can ask what's the probability that we've got some collection of links that form some collection of triangles of different characteristics. So we actually look at the network and say what's the probability that we see these things form in various combinations. So let's just keep track of counts. So let's count the number of links with these characteristics xi, xj that form, count triangles with certain combinations of characteristics that form and so forth. And these are actually counting the truly formed sets of links, triangles, and so forth. So it might be that a link is formed directly because those 2 individuals wanted to form it, but it's also because one of the triangles formed that contained it, or maybe even several of the triangles. So it might be that a given link forms in several different ways. It forms at once directly and then also as part of triangles. And here we're going to keep track of the direct number of links that actually formed and the triangles and so forth. So we might actually be doing some double counting in terms of some of the links. And actually some of the triangles if they also form as part of cliques and so forth. Okay? So we keep track of these actual counts. And then let's let Kn be the product of the total number of a possible graph. So let's look at it, some j, which is a possible subgraph combination, like links of type with 2 pairs of characteristics, triangles with something. So we'll keep track of each of these different possible orderings. And so if we have a finite set of possible characteristics, we've got a finite set of these possible subgraph combinations, then we'll keep track of how many of these could have formed maximally, how many did form of J, and keep track of the number of ways we could have done that. So S bar N J choose Sj, that gives us an idea of how many of these different configurations we could have had of links, say, of people who have both wealth level 5. So we can keep track of how many of those links are possible, how many actually formed, and then keep track of the many different combinations that we could have formed that. Take product over all these different J's, and that gives us a relative number of what's the statistic we saw, and how many different ways could we have generated that statistic. Okay? So it's just a combinatoric number, which tells us relatively how many different ways could we have gotten the statistic that we actually generated. And then there's variations on theorems like this in work by Carter Butts, Mele, work by myself and Arun Chandrasekhar, and I'll just present the theorem from this last paper. And what this shows is, under this kind of formation process, the probability that you're actually going to observe a particular statistic S is going to be then proportional to an exponential. So basically these theorems in these different papers aren't expressed in this form, but they show that if you're forming different subgraphs in some formation process, then when you can aggregate up, you can end up with an exponential representation of that. And so this is one where it's actually a SERGM representation. So we say that the probability of seeing a given count of links, a given count of triangles of certain types, of cliques of certain types, is going to be proportional to this weighting factor K, which counts how many different configurations we could have had, times this exponential, where now we're multiplying each of the counts of the actual subgraphs times these B's, which represented the base probabilities. And so this forms an exponential random graph models with these particular weights, which are the base probabilities. So going through and estimating an exponential random graph model then estimates this function, which then allows you to impute what the values, the relative values in terms of utilities were if you have some specification of the distributions of the error terms. Okay, so this gives us a tie between a simple network formation based on strategies where people are choosing what they want based on utilities and the exponential random graph form. The interesting thing, this is also what's known as a potential function. And what does that mean? That means that when you look at a given link and you think, or a triangle and so forth, and you think about whether it should be added or not, it's going to be added if the overall base value of this is a positive number and not if it's a negative number. And so this gives us then or a formation where we can sort of add up the values and keep track of that. And as the noise is sort of reduced here, what this reduces to is basically networks where the subgraphs are going to be formed where these values are positive. So as we scale up the B's and take away the noise in terms of the F's, we're going to end up with situations where the ones that are formed are going to be ones that tend to have positive values on these things, and the ones that won't form are going to be the ones that have negative values on these. So when we look at this, these exponential random graph models allow us to really bring in strategic models and fit them into this form, so we can fit strategic network formation inside of these models. And it opens the possibilities for sort of systematic estimation of different preference parameters and welfare analysis of some of the networks. Right now, the way we just talked about this, we could build it up on, say, links, triangles, cliques, and so forth. We might want to think of other models that have richer structure in terms of the network structure. So when we look at the formation in terms of the strategic models, those have been based on things like the connections model where you got delta, delta squared, delta cubed. You were getting value from much longer paths. That's not included in this particular representation, which truncates things to small graph structures where people are generating utility. So we might still want to enrich models that begin to allow for people to care about very distant paths, or other things in the network, or care about how other people are connected and what kinds of shapes are out there. So there's still a lot to be done in terms of building bridges between some of the strategic formation models and the random network formation models. But this gives us one recipe where we can begin to see some interaction between these. And so I just wanted to tell you a little bit about how we can begin to marry the strategic models with the exponential random graph models.